So another important thing that we'd like to look at when considering a situation like this is the variance or the standard deviation. So we'll go ahead and add variance to our table. And variance is, we'll abbreviate it as var of x. And the formula for variance is pretty important. The formula for variance looks like this. It is sigma, or the sum, of all of the of each value of the random variable minus the mean, which in this case for us is negative 1.34. And then you take that and you square it, and you multiply all of that times the probability of the random variable, a particular value of the random variable. So this is the formula for computing the variance. We sum together the value of the random variable minus the mean, and then square that, and then multiply that times the probability of the random variable. Let's take a look and see what I mean. So in this case, for this first one, we'll take our x value. Our x value is 95, so we'll do 95. And then we will subtract our mean, which is 1.34, so minus negative 1.34. And then we'll take all of that and we'll square it, all of this stuff. There we go. All of that gets squared. So we subtract 95 minus a negative 1.34, and the result of that we then square. Then you take all of that and multiply it times the probability of the random variable x when it equals 95. And so in this case we'll multiply by 1 over 52. So that gets us, so all of this multiplied together gets us this one value. And I'll repeat just to make sure you get this. So I'll walk you through one more. So let's say we want to find the variance. Let's say we want to find this term, the variance for this term, or this. We'll find this term in the variance, and this whole thing, this whole sigma is the variance, and this guy here represents one term at a time. So to find this one term for this stuff, let's go ahead and put it together. So we'll have the value of the random variable, 5, minus the mean, 1, negative 1.34, and then we'll take all of that, 5 minus all of that, and then we'll square it, and then we'll multiply that result by the probability, 3 over 52. Alright, so if I subtract, if I do 5 plus 1.34 and I square that and I multiply by 3 over 52, I'll then have this term right in here. I'll have this term that's associated with these pieces of information. And I want you to repeat that process for this guy and for this guy, and then in the end we're going to see if we agree on what the value is that we should get for the variance. Go ahead and pause the video and complete the calculations. So if you did everything correctly, in the end, if you found this term and this term and this term and this term, and you added them all together, because that's what sigma means, then what you should have gotten is 190.5 approximately. And if you did that, then we can go and we can attack the standard deviation. And the standard deviation is abbreviated SD of x, and it's a little bit more simple, because once you have the variance, all you really have to do is this. You just take the whatever the variance was, and you take the square root of it. So take the square root of the variance, and we'll have the standard deviation. And in this case, the square root of the variance is, let's see here, that's equal to the square root of 190.5, and in this case it gets us about 13.8. Now, one thing I want to make sure that I'm very clear about is when we go to take the variance, when we go to find the standard deviation, we don't need to go term by term like we did for the variance. For the variance, we had to calculate this, and then this, and then this, and then this, and then add them all together. For standard deviation, we just take this amount and we take the square root of it. It goes right there. That's it. And then that gets us the standard deviation. Now, once again, I'm going to ask you the question, what is the meaning of this 13.8? I want you to think about it in the context of this overall problem. What does it mean to get a result of 13.8 like that? Go ahead and pause the video and then I'll tell you. Well, first of all, the 13.8 is really $13.80, just like the expected value, just like the mean was. The mean had units of dollars, and the standard deviation has units of dollars. And so what this represents is that although if we gambled again and again and again playing this game, our average result would be a loss of $1.34. The variation that we get, one standard deviation, could be $13.80. That means we could go $13.80 higher than this or $13.80 lower than this, and that would be one standard deviation in either direction. Now, if you recall from our discussion of normal distributions, if we look at a normal curve for a normal distribution where we have a mean of negative 1.34 and a standard deviation, which again, remember, you usually graph at the inflection point on the normal curve. If we have a standard deviation that is 1380, so 1380 out from here to here, I guess we could call that our sigma of sorts, our standard deviation, although we do refer to it differently now that we're talking about expected value and random variables. We'll just refer to it as our standard deviation like this. So anyways, this amount here would be 12 something. I can't remember exactly what, 12 something. Anyways, so if you recall, in between here and here, for this area here, this would end up being about 34% of our entire probability. So the probability of ending up somewhere in this area between losing $1.34 and gaining $12, that would give us $12 and something. That would give us about 34% of the entire normal curve, or there'd be a 34% probability of ending up somewhere between here. So the idea of how much might we win if we played this game over and over again, there is the possibility that if let's say this is approximately where breaking even occurs, that you can see that between these two you might have some, who knows, 10, 15, 20% possibility that in this area, probability that you could actually either break even or win something. So having the standard deviation in addition to the expected value is pretty important. And I wanted to make sure that we could tie it back into the normal distribution that we studied before, since we do have a mean and we do have a standard deviation.